So I will use a proxy for the operator norm. Some people use the Châtain P norm. For some reason, I prefer this proxy. So let, I don't know, H beta of M be 1 over beta log trace E beta M. When M is a symmetric matrix, you can see that the maximal eigenvalue lambda max of M is less, and beta is some positive parameter. It's less than H beta of M, and this is less than lambda max of M plus maybe log n over beta. So if beta is more or less log n, H beta of M is more or less the maximal eigenvalue up to some additive constant. Okay. Okay, so recall dAt is some yeah, it's yeah. So recall like the expression for the derivative of at, where hi, so it's hi t is integral x minus at. I x minus at to d mu t. And then apply Ito. To H beta of AT. Okay, so you will get D of H beta of AT equals so grad H beta of AT dot sum hi twi plus or minus, you will have this term here. At square. And then you have Ito's term. Okay, so Ito's term, this is why I wrote the matrix here. So Ito's term will be the Hessian. Okay, what's the quadratic covariation of this guy? So this is Ito's formalism. The quadratic covariation is, or the derivative of the quadratic covariation. You see that it's sum hi square dt.
Excuse me, what was that? It's covariation. You wrote like a product.
Yeah, this is some informal. Okay, maybe I should. Plus, it's not actually not good the way I write it. Ça, c'est pas bon. Okay, this is 1 sur bêta, log, somme, exponentielle, bêta, lambda I. These are non-negative numbers. So this is larger than if I just take 1 sur bêta, log, larger than. No, it's fine. No? And if I want an upper bound, I all upper bound them by exponential beta lambda 1. Okay. Okay, here this was wrong. So here what I meant to write is that when you have what is Ito's formula? Ito's formula for some martingale of this type will tell you that if you want like in general the Ito's term, so you have this 1/2 the Hessian of your function, so which is h beta. So at the point 80. And then what you do is that you somehow you need to apply it to some HIT dwi, some HIT dwj, HJT dwj. And Ito's formalism is that the cross term will vanish, okay, and you will be left with half Hessian h beta of AT HIT dt, and there is a sum. Yeah, maybe let me deal with this second order term. So h beta of m is 1 over beta log exponential, trace exponential beta m. So, okay, if you grad h beta of m applied to some matrix H, okay, will be trace E beta m. So this is some log derivative. H divided by trace beta m. Okay, if you want the grad H beta of m is E beta m divided by trace beta m. So this is some positive matrix with trace 1. So in particular, trace H beta of 80 square would be non-negative. Okay, so this term here, over here I will just throw it away. So for the second derivative, you will get the second derivative of this guy, okay, and then some negative term because the log is is so in the same way. So when you do H beta 80 HI. So here I will skip some details, but here I will use, so I will have one term from this trace exponential beta m, and then one term from the log. So the term from the log will give me something negative, which I will throw away. And the term from the Hessian of trace exponential m, I will upper bound it with my lemma. Okay. So so that was the matrix lemma number 2. And then I'll get, okay, maybe the beta pops out. And I'll trace of this matrix. HI square. So at the end of the day, blah, 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 you get dh beta of 80 up to some negative term that I will throw away. You get trace grad h beta a sum hi dbi minus plus beta over 2 trace grade h beta of 80 sum hi square dt. Very good. Ah, c'était W. Okay, so I've computed the derivative of this proxy for the operator norm. I have some martingale term, and I have some dt part. Okay. So maybe let's try to deal with the dt part first. Okay, this is, as I said, so this is a matrix of trace 1, positive matrix of trace 1. Okay, so this is less than the trace 1 and positive. So this is less than the operator norm of some hi square. And here you see some expression that was in my 3 tensors lemma. Okay. So in my convention, this was 3 tensor lemma number 2. This is less than, so let me think. So there was a constant. There was the operator norm of mu t, like the operator norm of the matrix. Okay, maybe recall. So hi is integral x minus at. Okay, so here you have Cp of mu t times the covariance of mu t square. Okay, this is what you get from the 3 tensor lemma. Okay, so far so good. And then I continue, and then here I use improved Simonovits. Of Boas, which tells me that since mu t is t uniformly log concave, the Poincaré constant is at most the operator norm to the 1/2 divided by square root t. Okay? So 1 over square root t, at 3/2. Okay? All right. It's continue here, okay. This is upper bound for trace grad h beta a sum hi square. Okay, so I'll keep this. So what about the dBt part, dWt part? Okay, so this is some martingale. Okay, so you have some trace. Maybe I should give a name to this matrix. Mt equals grade h beta of 80. So trace mt hi dwi. Yeah. Oui, il y a du vrai dans ce que tu dis. Hop. I don't care because I will. Okay, you will see. So what is the? So let's call dZt this martingale. So what is the quadratic variation of Zt? Okay, so it's sum trace mt hi squared. Okay, dt. So now what is the sum trace mt? Ouais, si les m et les h sont pareils, mt hi squared. I want to upper bound this. So this I can see it as it's some Euclidean norm. Okay. So let u be a unit vector. Sum trace mt hi ui. Oui. Yeah, sometimes I will lose some variables. Okay, so this, if you can interpret this as this is trace mt h. Yeah, notation are awful, but HUT, where HUT is sum UI HIT. Okay, so this is, if you write everything x minus 80 dot u, x minus 80 tensor to d mu t. So this is smaller. Again, this is a positive matrix of trace 1 and the operator norm of HUT, which is smaller by my 3 tensor number 1. Some power of the operator norm of the covariance. And the power should be this is three homogeneous, well, 6 homogeneous in the measure, so this should be 3. Okay, summary. Okay, the operator norm of AT is less than h of beta of AT, which is h beta of A0 plus okay, the integral of d h beta of AT. Yeah, I made something wrong here. Yeah, something is wrong. Let me see. So actually the power of A won't matter, but it's better to write correct things. Okay, I'm lost in my notes. I think I can, maybe I will have to yeah, it was 3/2, yeah. Yeah, no, so this was, at this stage it was 3/2.
You didn't finish the left part where there's a question mark. There's a square. This is a question.
And so for any unit vector, yeah, I think, okay. So for any unit vector, so maybe let me continue here. So yeah, so for any unit vector, this quantity less than this, so the Euclidean norm of this is less than the square of this, which was the, so yeah, I think it's correct. Up to a constant is less than 80 cube dt. Now, there was a summary. Okay, so this is less than, okay, so A naught is the identity, okay? So h beta of the identity is log n over beta. Maybe I wanted to do it a bit differently. Okay, let's see, maybe it will work. Plus, and here you have two terms. So plus, okay, the dt part first is something along the lines of integral from 0 to t of there is a constant 1 over square root s times where is it? Here, times at the phi half ds plus the martingale part. Let me call it zt. Well, Zt is some martingale starting from 0 and satisfying the quadratic variation is less than integral from 0 to t some constant as cube ds. So it looks like I'm in bad shape because somehow I want to upper bound the cooperator norm of A, but like my upper bound depends itself on the operator norm. But thanks to Friedman inequality, to this stopping time strategy, I can actually find a way around this. So assume that there exists S, so fix t smaller than, or fix t, some t, and assume that there exists S less than t, such that the operator norm of AS is at least 2, and choose S to be, let S be the smallest such time. So the operator norm of, I don't know, AU is less than 2 before S. Or you introduce the stopping time, whatever. Then, okay, so here I will prove something too strong. I forgot the beta. I'm sorry. There was a beta here. Yeah, I need the beta. Maybe a longer chalk. Because if I forgot the beta, then I can prove KLS, so it's too easy. So the beta, it came from the derivative of my proxy for operator norm. So there is no free lunch, you know. It's like you need to take beta large enough to kill this log n, but somehow you have to pay for it at some point. So if I forget the beta, then it doesn't make sense. Okay, so choose beta equals 2 log n or so. Then you see that AS, which is in norm at least 2, well, which is equals to, it's smaller than Now maybe beta equals log n is fine. 1. Ah, no, c'est ça, yeah. Okay, I made a mistake. Sorry, that 1 plus, yeah, I was confused from the beginning. So 2 log n. I'm sorry, it's kind of a mess, but by the way, there are some notes on the website. With presumably less typos, but I don't know. Plus, okay, so if I'm at some time s, where this AS will be smaller than 2, okay, by definition of my S naught here. So here I have some constants. And then the good news is that 1 over square root s, it explodes, but in an integrable way. So square root s. Well, I've used s and t. Yeah, sorry about that. And there is beta, and beta, I say it's 2 log n, but I can absorb the 2 in the constant. Plus zs. Now you start to see like the 1 over log n squared, right? So this is less than 3/2 plus, actually, it's a bit confusing with this s and this t, but s is less than t log n plus zs. And this is smaller than, who cares? So can you give me a number that's somehow between 3/2 and 2 at this time of the day? I can't.
31 over 20.
31 over 20 over 20 plus zs if t is sufficiently small multiple well, no, okay, too long. If t is smaller than log n squared, and okay, and with a large enough c here. Moreover, it's not over, but it's nearly over. If, moreover, by definition, Zs, which is less than integral from 0 to s some constant a u q u, is less than some constant times s, which is less than c prime t. Which implies that Zs is at least, so here, okay, it implies that Zs is at least, yeah, you are not very nice to me with this 31 over 20, but 19 over 20, right? No. 1 over 20? Okay, I'm completely confused. Okay. I'm making a fool of myself. So, probability that there exists And then I can conclude by Friedman. Done. Sorry, this was a bit of a mess.
Where on sigma square and what you had in Friedman?
No, I had sigma square, so no, it's fine.
MS instead of limits?
Yeah, this was called Z. So let me sum things up. When you look at the derivative of MT, because of this three tensors inequality, well, the derivative of your norm is bounded above by something that is somewhat order 1 if t is smaller than log n square inverse, plus some martingale term. And now the kind of thing that's somehow difficult to handle, it the difficulty is your martingale term, the bound that you have for the quadratic variation, it also depends on the operator norm. But by some stopping time argument, you can somehow make this work. And actually, if you want this martingale term, it doesn't play a role. It doesn't. It's like you can, if you think about the argument for a minute, you can actually see that this is not the bad guy. Actually, this one will never trouble you. It's really the dt part, this part that comes from the Hessian, the term sum hi square. That is really the bad guy in this story. So, I mean, if you find a more clever way to bound this type of three tensors, then you could improve it. Okay. So really, this is the message, and maybe as Boaz mentioned this morning, you have lots of variation of this. Yeah. Yeah, but the thing is that, okay, maybe I made a mistake, but okay, I could have just taken expectations, that's what you're saying, and just don't care about martingale. Yeah, the problem is that if I just take expectation, I will get something along the lines of expectation AT less than, I don't know, 1 plus some constant integral from 0 to t expectation AS cube ds, and this I don't know how to handle it.
Oh, is it because this is already conditional?
You see, so I'm sort of this type of thing I can. The problem is that I have a larger power here than here. If I had just 80, I could do it like you're saying, but this is the problem. Or maybe I don't know 2 or whatever. I want to make some comments. So one remark. There's alternatively so in my argument, I used improved Lichterowicz to bound the Poincaré constant of mu t. And I could have, instead of Cp mu t less than At over square root t, I can say Cp of mu t is less than Cn. Yeah, there's a 1/2 here, sorry. At, where Cn is the worst is sometimes what is called the KLS constant. Largest Poincaré constant of an isotropic log concave. This would lead to E of AT is O of 1 up until 1 over some constant times Cn again, as Boaz mentioned. And hence, but actually, if this alternative bound is good enough also for the, this is what, this morning Boaz, he had this proof 1, proof 2. So this gives you, it gives you, it works because, so it looks like you're chasing your tail, but actually it's fine because it will give you something along the lines of Cn is less than square root n, square root Cn log n, which also implies, up to constant. So it also gives the log n bound. This is alternative bound. Maybe other comment. Okay. Yeah, maybe I don't really have time. Okay, I'll only say a few words of this. So life before improved Lynch-Lerovitch. So this was a lot harder, but for a limited number of people though. But so the issue is that okay. So just maybe I'll say a few words about the Eldan paper 14. Okay, so the thing is that when Boaz showed us this argument this morning, he was using improved Lynch-Lerovitch. So there is a variant of that argument that tells you that if expectation AT is O1 up to time T naught, then Cp of mu is less than 1 over T naught. So using not improved Lynch-Lerovitch, so I don't know how to call it, usual Lynch-Lerovitch. Okay. First step. Now, second step. If you do this, then you're with. If you do this, then you will get Cn less than Cn log n, which is not particularly interesting. So, what Eldan did instead is that recall remark after so this was after 3 tensor bound number 2. So after three tensor bound number 2, there was a remark that said I only applied Poincaré to some quadratic function. So if you implement that, you see that you can somehow you can replace Cn by C tilde n here. Here. Where C tilde n is like the KLS constant, but only for quadratic form. And you get some, and then if you go back here, you will get Cn less than log n C tilde n. So it was like some sort of conditional statement. Like if you know KLS for quadratic form, then you have KLS for whole function. Actually, there was an additional ingredient in the Eldan's analysis. Which I don't have time to spell out, where because this Poincaré constant for quadratic form, he was not so pleased with it. It seems, or so it seems. He wanted like just for the because there was a popular conjecture at the time that it was Poincaré, but only for the Euclidean norm. You don't want to allow all quadratic form, just the Euclidean norm. And somehow he was able to find some variant of this that gives Cn less or equal than log n squared. So he had to pay another log n here times something that I will call Sn, where Sn is like the KLS constant, but this time only for the Euclidean norm. So here maybe I can. So this is the supremum of the variance of x, so Euclidean norm of x log concave are isotropic. Like the conjecture is that this constant Sn should be bounded. This is called the thin shell conjecture. This was mentioned by Boas because it's connected in connection with the central limit problem for log concave vectors. And this is of course a particular case of the KLS conjecture because you're only asking to have Poincaré, but for a very specific function, not every function. So this is called the thin shell constant. So this is the result of Eldan was thin shell conjecture implies KLS conjecture up to a log or a polylog. And I think that's enough for today. I wanted to say something else that I have some